Okay, this video is to show you how to do the third or hard level of the DC node equations tutorial in Circuit Tutor. So as usual, you might want to look at an example, which would be a good idea. So I'll just show you briefly an example here. And what's new now is we actually have the concept of a supernode, because now we have multiple voltage sources which are not connected in a chain. In other words, they don't share any common nodes. And so I actually have, in this case, two voltage constraint equations, which can be explained here if you need detailed explanation of that. We have KCL equation, in this case, for node 1, okay, which is this one. And then we have a KCL equation for node 2. Neither one of those nodes is connected to a voltage source, so they don't pose any problem. But the trouble is, suppose I wanted to do it for node 4. Now, if you think about it, I could easily find the current going here. I could find the current going here, the current going here, and the current going here. But what about the current going through the voltage source? Well, we know that the current through a voltage source is whatever it needs to be, which means we don't really know its value right now. And therefore, we cannot write a KCL equation for node 4. And we have the similar problem for node 3. And in fact, we have the same problem for node 5 as well, because it's connected to a 2-volt source and the reference node. But of course, we never write a KCL equation for the reference node, so that's not a problem. But we basically skip the one for node 5 because it's just a single node there. But that's replaced by a voltage constraint equation. And we do also get a voltage constraint equation here that replaces one of the equations, but it doesn't replace the equations for both of these nodes that we cannot write. So we still need to do something else, and that is called forming a supernode. So as I click next here, you notice that now we're actually considering both of these nodes together to be the surface that we use in Kirchhoff's current law, meaning that the sum of the currents exiting any closed surface in a circuit must be 0. And the closed surface doesn't have to be around a node. It can be around, in this case, around 2 nodes. So our surface, you can imagine, kind of going here, 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 and here. That's a closed surface, okay? And so the sum of the currents going out of that closed surface does not include a current going through a voltage source whose value we don't know. Therefore, we're able to evaluate that without having to know the current through the voltage source. And so now we add up these 5 different currents that are leaving the supernode, which is comprised of both nodes 3 and nodes 4, as well as the 5-volt source that connects them. And you could also have multiple voltage sources in a supernode too, but in this case it's just one. And those sum to 0. Then there's also the power absorbed by a current source, and that requires knowing the difference of voltages multiplied by its current, and you have to use the passive sign convention. So there's several new things here, the main one being the supernode and also the equation for power of a source. And of course you can get some explanations here if you need that. Okay, so let's do an actual problem at the hard level. So the first step, as always in nodal analysis, if we've already identified the nodes, which we have here, is to choose a reference node. And here I want to choose one, as is usually possible, connected to a reference node, because that makes things a little simpler. So I'm just going to choose this one here, or you can choose it over there. It doesn't matter. It's the same thing. And I'll click OK. And it's actually placed the ground over here, but of course that's the same node, so it doesn't matter. Okay, so now, again, it's advising us to do the voltage constraint equations first, and then probably actually the sought variable equation would be a good one to do as well. So let's write voltage constraint equations. Okay, and again, I apologize for this being messed up here. That's an artifact of my video recorder. That's not something in the program. But okay, so let's do it for the 3-volt source. So that connects 2 non-reference nodes. So that'll be a difference of voltages now is equal to the value of that source, which is the 3 volts. And so specifically, that's going to be V5 minus V3, because V5 is connected to the positive side and V3 is connected to the minus side. So that's going to be V5 minus V3. And I'll check that, and that's correct. Now I have to do another voltage constraint equation, as it's telling me here, for the 1-volt source. That one has one node, which is ground, and so therefore it'll just be a single voltage equals to the value of the source, which I enter as 1 volt. Now in this case, this is V1, but V1 is actually equal to -1 volt because it's the plus side of the source connected to ground. The minus side is connected to V1. So therefore I need a minus sign there. And I'll check that, and that is correct. So now I'm done with the voltage constraint equations, which are some of the simpler ones. And I'll also do the SOT variable equation while I'm at it, because that's also a simpler one, before I do the more complicated KCL equations, where it might be easier to make mistakes. Okay, so it's warning me here to do the SOT power that there's actually 3 pallets of terms that I might need for that current source. In fact, well, we'll see if I need them or not, but you might. And wait until that's done flashing, and so you can see those other palettes like this. So we just click on those radio buttons to see those, because they wouldn't all fit on one screen. Okay, so of course we have the absorbed power in the 4 amp source, the one with the gray label there, equals to what? Well, it's always voltage times current, so the voltage across that source is a difference of excuse me, node voltages, but it's not divided by resistance because there is no resistor there. So in fact I need this term, and it tells me actually if I hover over that it's the power of an independent current source not connected to ground. So that tells me kind of that that's a clue. Okay, so I want the power absorbed by that, and therefore I want to use sort of the passive sign convention with respect to the direction of that. So it would be V2 minus V4 times the 4 amps. And so basically this voltage is such now that the current flows into the plus side of that voltage, meaning a passive sign convention. So for absorbed power, you want to use passive sign convention, then you'll have a plus sign here. If I wanted to make this V4 minus V2, I would have to put a minus sign here, or I suppose I could put it in the current, but it's got to be there somewhere, or I could put it over here also, but there's got to be a minus sign in there. Okay, so that's correct, and now I've done all the SOT variable and constraint equations, which is usually best to do first. Then I'm going to do the KCL equations. So I'll select the Kirchhoff current law equations here, and now I need to write an equation for every node that I can. So you notice node 1, for example, can I do that? Well, no, unfortunately, because it's connected to a voltage source, and we don't know the current through voltage sources, so there's no way to write a KCL equation for that. But because that actually goes to the reference node, I don't need to make a supernode there. It's sort of like you might call it the reference supernode. So we don't need to do anything about that. And we already have a constraint equation that will take the place of that KCL equation. Now for node 2, we need to write it because there are no voltage sources, as you can see, connected to the magenta colored node 2 here. So we have a resistor not connected to ground, so we'll need that term. We have an independent current source for this term, another resistor not connected to ground, so that, and then yet a third resistor not connected to ground, so that would be that one. And the sum of those is all 0. None of those are directly connected to ground. So now the current through the 1 ohm resistor is going to be V2 minus V1, or 1 ohm, using the passive sign convention as always. The current leaving V2 node through the 4 amp source, well, that's just 4 amps because that current source is in fact making current leave, or making charge leave really. And then I have V2 minus V4 for the current coming down here through the 4 amp source, again leaving that node, and that would be divided of course by the 4 ohm resistor. And the final one through the 9 ohm would be V2 minus V5, because that's the voltage on the other end of that element, and that's divided by the 9 ohms. So that's the complete equation for node 2. And again, if you want to use currents entering the node, you can, but you'd have to put a minus sign in every term in the equation then to do that. Okay, so now what about node 3, let's say? Well, can't do it for node 3 because it's connected to a voltage source. How about node 4? Well, yes, we can do it for node 4, so let's do that. And we're going to have 3 resistors. One is connected to ground, the other 2 are not. So we're going to have 2 of these, one of those is not connected to ground, and finally a independent current source. So we have 4 terms in this equation. And notice that, for example, when we wrote this, because it was for node 2, V2 always has a plus sign, and the other node voltages all have minus signs. That's always going to be true when you add currents that are leaving a node. So that's kind of a convenient way to do it. That way you can kind of check immediately if you got your signs right. Okay, so here this is V4. So it's going to be V4 minus V3 divided by 7 ohms. And then the current up here is going to be V4 minus V2, which is the voltage on the other end, divided by the 4 ohms here. And then the current going down to the 5 ohm is just going to be V4 minus 0, or just V4, divided by the 5 ohms. Again, using the passive sign convention as always for currents through resistors, if possible. And then the current leaving through the 4 amp source, well, that's actually a negative 4 amps, isn't it? Because the 4 amps is actually entering. So that has to have a minus sign. So if we check that, that'll be correct. And so now we're done with node 4. And node 5, well, that's also connected to a voltage source. So we can't write a KCL equation. But if you look at it, we only have 1, 2, 3, 4 equations, basically. But we have 1, 2, 3, 4, 5 node voltages. That's not enough equations for the number of unknowns, is it? So that means we have to use the supernode idea for this 3-volt source. So we're going to form a supernode consisting of nodes 3 and node 5 that are connected by a voltage source. That's always how you get a supernode, is things that are connected by a voltage source. So we're now going to write another KCL equation for that, the same way we did before, but now we have to consider the currents leaving both this node, not through the source of course, and leaving this node. So that's actually going to be only 3 terms. So one is going to ground, so we'll have this. One is not going to ground, so we have this. And the third one is not going to ground, so we have another term like that. And that's all the currents that actually leave that supernode. Okay, the internal currents we don't worry about because they're both leaving and entering, if you will, so they basically cancel out. Okay, so we have V3 divided by the 7 ohms. That's the current leaving through this resistor. And then we have V3 minus V4 divided by this 7 ohms. And then finally we have V5 minus V2 divided by the 9 ohms. That's basically the voltage difference using the passive sign convention, as always, for Ohm's law, where we can. That's the current that's going to flow this way through the resistor from high voltage to low voltage. Remember, that's called the passive sign convention. Now notice that this equation is a little bit different in that sometimes we have the V3 node as the positive terms, other times we have V5. And that'll generally be true for a supernode, is that you can have more than one variable with a plus sign. But the nodes that are not part of the supernode are going to always be the ones that have minus signs. So it still follows basically the same pattern as it does for a single node. Okay, so that is correct, and we're now actually done writing those equations. So we just say no more equations. And where the cheering stops, then basically we're done. And we can also see a detailed explanation if we need that, where you can get a really detailed explanation of each KCL equation or more detail about constraint equations. And we can cycle through that if we like to understand the structure of the equation, just to make sure we understood what we did. Now, if you don't need that, that's fine, but you have the option to look at that. Okay, so that would be it for level 3.